All right, class, we are going to begin 1.5 today. Notice the title says more on identities. And so because of that, we have to kind of go back real quick here to 1.4. This is going to be a super quick review and just connecting the dots together so we can keep on going. Okay, so let me go back real quick here. This is review review of 1.4. So let's quickly, just super fast here. And if you want to write this down, that's fine. If you don't want to write it down, just kind of pay attention to this part, that's absolutely fine too. All right, here I'm going to write down our trig definitions, the way we would define our trig identities there. And so my suggestion, if you were absent for 1.4 lecture, you may want to write this stuff down, just to have it for your notes. So sine theta is defined to be y over r. Yep, that's true. Cosine theta is x over r. Tangent theta is y over x. Then we have some other identities like cosecant theta is equal to r over y. And then we have secant theta is equal to y over x. And then we have cotangent theta is equal to x over y. And the question I had for the class when we started this is, do you see any connections here? Is there anything that's sort of connected to itself? And the first one you probably should notice is this right here. Notice that sine theta is y over r, and cosecant theta is r over y. So hey, I see a little relationship there. Aren't these guys just reciprocals of each other? Yep, and actually, hold on. So is these two. Okay, and so are these two. Okay, boom. So let's do this here. We're going to actually list those, but first I just want to prove one of them. I'm not going to prove all of them, just one. It is the proof. I think that's how you spell proof. Yeah, proof. So I'm going to prove that 1 over cosecant theta is equal to sine. That's what I want to prove right there. That's going to be proof. Okay, so how do I start off with the proof? I go like this. I say 1 over cosecant theta is equal to, by definition now, by definition is r over y, every good there. And then we have this little thing from math earlier on. You guys should notice that if you have like a 1 over, let's say 3/4, right? That just means reciprocal, and that means you get a 4 over 3. True. So over here, notice we're going to get the same thing here. 1 over r over y. We are going to get a 1y over, which is actually sine theta. That is it. That's how you prove all these identities right there. Okay, so now we're going to connect as many as we possibly can. So there's one. And then also, how about the other side of it? So hold on, 1 over cosine theta is equal to sine. That means that 1 over sine is equal to cosecant theta. So there's 2 right there. All right, if you connect from the previous slide, thinking there's going to be the cosine theta. There you go. Oh, let me write it the way so we kind of keep things in order. So 1 over secant theta is equal to cosine theta. There's right there. If you can kind of see, it's going to be the x and the y values. Perfect. And let's go the other way. So 1 over cosine theta is equal to secant theta. Next, towards the bottom of the page here, and now we have 1 over cotangent theta will give us tangent theta. There. And then 1 over tangent theta is equal to cotangent theta. Okay, there it is. There is, we actually call them reciprocal identities. There are 6 of them. And that's it. Give you guys a little time to finish up. And again, you can pause the video if need be to make sure that students are caught up with that. That's cool too. Be no problem. Okay, then we have this other one. It's kind of interesting one. We have something called the ratio identities. And so we'll get the names a little bit later on, but think about this right here. If I have something called sine theta over cosine theta, if I just make a fraction of these two right here, by definition, I have y over r, and I have x over r by definition. But that's a complex fraction from mathematics. So if that happens, I know I can always do this. I keep the top fraction exactly the same. I change this to multiplication instead of division, and I do this. And the r's are gone. They cancel each other out. And then the question is, which trig function is this? And it is tangent. And all we're doing is we're just making as many connections between our trig functions as possible. That's what we're doing. So there it is. I have a ratio identity that says sine theta over cosine theta is really just tangent. So hold on. Don't we also have a reciprocal identity? Hold on. So if tangent is sine over cosine, that means cotangent. Let me write it the way. Cotangent would be this right here. We could prove it if we wanted to. I just don't want to. So we're just going to go with this right here. So there it is. If you flipped sine and cosine over, did the same exact proof on top, you would wind up with cotangent. Okay, so real quick here. So we have 6 reciprocal identities. Boom, boom, boom. We have 2 ratio identities. And then the fun one. Fun one is Hipparchus sitting, like I said, on Saturday morning. It was raining outside. He had nothing to do. So he was thinking this whole idea here. If I have theta, and if I have x, right? This is how we define our trig function in the first place. This is x and y. And we have r, right? And a lot of times what we've done is we've made r to be a 1. True? So a lot of times, not always, but a lot of times if we can, we try to make r 1 because it makes life a little easier. And then you start thinking about this one concept here. So hold on. This is my x coordinate, right? So wait a minute. If cosine theta is defined to be x over r, and if r is 1, well, if this is the case, then this is true, isn't it? That's true. And then if that's the case, then that means this is true. If r is equal to 1, only in this special case, cosine theta is actually equal to the x coordinate. And the same thing for the y. So hold on. So sine theta is defined to be y over r. Whoa. That means sine theta is y over 1, which really just means that sine theta is equal to 1. Now this only, not 1, to y. Now this only happens if we are, where we have r is equal to 1. Okay, so this is so cool. Hold on. So again, Hipparchus, Saturday morning, right? Nothing else to do. So that's 1. And this is going to be cosine theta. This is sine theta. I have that relationship going. And then Hipparchus sits there for a little while. And then he realizes something awesome. Like, you know, like those light bulb moments that you have? It's like you're sitting there and you're like, oh man, I just figured this out. So Hipparchus is sitting here and he says to himself, hold on, wait. Is this a right triangle? Doesn't this fulfill a Pythagorean theorem? So hold on, if I do this, that means if I take the x coordinate and I square it, I take the y coordinate and I square it, and I add those together, that should give me 1 squared. That fulfills the Pythagorean theorem. There it is. He just developed a whole new set of ideas in trigonometry. Now, some notation here real quick here. If I drop these parentheses, if I do drop the parentheses, notice what happens here. I go like this, and it looks like I'm actually squaring theta first, right? Like I don't want that, okay? So what I want to do, I want to write this without parentheses because it just looks a lot cleaner. So what we do is we write it like this. We say cosine squared theta. And the square is now on the cosine instead of the theta. And it just looks cleaner. That's it. So there it is. So I'm going to rewrite it in just a second here. Okay, that's perfect. Invented a whole new set of ideas in trigonometry. The only thing is we personally like sine to be going first. And tradition. I think we started writing it like that way, and everybody kind of kept on writing it that way. So we have the Pythagorean theorem identity. Now, the only thing with this one, notice this is an equation. And if it's an equation, actually I could put this sort of a few different ways here. So if we subtract cosine squared from both sides, I get myself sine squared theta is equal to 1 minus cosine squared theta. And that is just a different variation, but pretty much is a different way to view that. Okay, so hold on. If that's the case, that means I can take a square root of both sides because I had algebra 2 with Mr. Grant. And I can write it like this. So notice off this one equation, actually there's two different variations. And then instead of subtracting cosine squared, I can subtract sine squared. So wait a minute. I can write it like this then. 1 minus sine squared theta. Okay. And then I can take the square root of both sides, and I can write it as plus or minus 1 minus sine squared theta. Okay, that is so cool. And Hipparchus, I don't know, Hipparchus. He is ecstatic. He's just beside himself. Like, I can't believe I have just invented some new stuff in trigonometry. And then he gets even more brainy idea. He says, look, wait. Hold on, sine. If I take sine over here, and then I divide everything by sine squared. So let's see. Let me move it to the next slide here. The next genius idea. Right there. He says to himself, you know, I have these ratio identities. Let's go back over here. I just made these ratio identities, didn't I? Sine theta over cosine theta is equal to tangent theta. Sine theta over cosine theta is tangent theta. So hold on, how about if I just do this? I'm going to divide here, instead of by sine squared. I'm going to divide here by sine squared. I'm allowed to divide as long as I divide both sides by the same thing. There it is. Dun, da, da, da. Just invented more new trigonometry because sine squared theta over sine squared theta is 1. Cosine over sine. Cosine over sine is cotangent. And it's a square because both of them are squared. And then what's the reciprocal identity of sine? Cosecant. Okay, so I got this relationship though. I got cosecant 1 plus cotangent squared theta is cosecant squared theta. This is super cool. Okay, so wait a minute. I need variations of this, just like I did last time here. So let's do some variations. I can take square root of both sides, right? So first, I guess we can move this around. So let's see. I'm going to take the square root of both sides. So that means you guys can do this in your heads here. I think you guys can move this around real quick here. Cosine squared is plus or minus 1 minus cotangent squared theta. There it is. I just took the square root of both sides. Give me this one. Okay, another variation. I can move this 1 over to this side. So I can make cotangent squared theta be just equal to cosecant squared theta minus 1. And if I have a perfect square, I can just take the square root. So I got plus or minus the square root of okay, so I have the main concept here, and I usually have, let's go back over here. I have the main equation, and I usually have 1, 2, 3, 4 variations. So let's come back over here. I have the main equation here, and this is 1, 2, 3, and I'm running out of space. But is there some kind of other variation I can make? Yeah, how about this? How about if I move the cotangent squared theta over to this side? So here's my fourth one. I'm running out of room, so I'm going to have to leave it like this. Here's my fourth variation. There it is. So I have 4 variations of the same one. Hipparchus, one more genius idea. Instead of dividing by sine squared theta, how about if I just divide it by cosine squared theta and see what happens there? And so we're going to go with, boom, boom, And let's divide this thing by cosine squared theta and see what happens here. Cosine squared theta. Boom. Cosine squared theta. And one more. Cosine squared theta. All right. Sine divided by cosine. What does that mean? Sine over cosine, sine over cosine. That is tangent. So tangent squared. These guys are exactly the same. They cancel. And the reciprocal identity to cosine. Bam. That's so awesome. Okay. Um, we need four variations, right? Here's my main equation. That's my main one. Give me the four variations. So first things first, since secant squared over here, I can just take a square root here, square root there. So first variation, secant theta is equal to plus or minus the square root of um, tangent. Notice they're adding, right? So this is addition formula here. Tangent square theta plus 1. Okay, what else can we do? We can move the 1 over to this side. So now we have tangent squared theta is equal to secant squared theta minus 1. And then we can take the square root of both sides. So plus or minus the square root of secant squared theta minus 1. Dun, da, da, da. One more variation. What can we do? Instead of moving the 1 over, we move tangent over. So tangent gets to be scooted over. Left with 1 is equal to secant squared theta minus tangent squared theta. That is so cool. Okay, so let's review just real quick, and then we'll go on to the next part. So based upon my definitions, I am able to make 6 ratio identities. And based upon that, I can make some ratio identities. There it is. Sine over cosine is tangent. Cosine over sine is cotangent. And there's 2 of them. And then, by the genius of Hipparchus, he allows us to make Pythagorean theorem. They're called trigonometric Pythagorean theorem identities. So I have 1. This is number 2. Technically, there's 3, right? But then we have variations for each one. And this one right here. Whoa, went too far. This one. Come on. And perfecto. There it is. Okay. That's just a quick review. What, a 12, 14-minute review of 1.4. Now let's jump to 1.5. So 1.5, and again, pause the video if you need to in order for you guys to write down all the instructions for the problems here. So 1.5, this is more on identities. We're going to do some more stuff. So exercise 1 says write each of the following in terms of cosine theta only. So now just getting to the concept of I just want it in terms of one trig function only. And we do that. That's, in a sense, sometimes called simplified, right? If you can get it to one trig function, you've simplified something all the way down. And so all those identities that we just covered, let's go with it here. And the more familiar you are with identities, the easier it is. So I would suggest maybe having them written out, and as you're doing the homework, just having a list right in front of you as you're doing all the homework, especially for 1.4 and 1.5. But let's go with it. So can I write secant theta in terms of cosine? Absolutely. It's the reciprocal identity. It is 1 over cosine theta, and I'm done. That's it. Yes, it is that simple. For B, a little bit more difficult, not by much here. So let's at least get close. So I'm thinking cotangent theta is, well, I know it is. I know it's cosine, right? Isn't it cosine or sine? Go back to my identities just to make sure. I think those are going to be my ratio identities. There it is. Cotangent is cosine over sine. Perfecto. Here it is. So cotangent theta is cosine over sine. The only problem is I still have sine over here. So can you transform sine into cosine any which way? Absolutely. Cosine stays cosine. But I have a Pythagorean theorem identity that says, and I'm going to just kind of switch between slides just so we have them here, just so I'm connecting stuff. This one right here, isn't sine theta same thing as plus or minus the square root of 1 minus cosine squared theta? Absolutely. So this will be plus or minus the square root of. So now notice everything is just in terms of cosine. Not that cosine is anything special, you know? But the fact that we want it to simplify it, so we're just using one trig function for our equation. That's kind of the point there. All right, let's keep on going. Give you guys a little bit of time to write things down here. So exercise 2, a little bit more, just a little different. So I want to do this here. Can you write each of the following in terms of sine and cosine? And then you're going to simplify it as much as you possibly can. Give you a little bit of time in order to write down the problem. All right, let's go with it here. So we're going to do a little bit of like pre-algebra-ish with trig functions. We're going to simplify stuff. So let's go with it here. So cosecant. So notice, I guess, a few things here. Notice cosecant theta is just listed right next to tangent. So if you kind of want to know what's happening here, there's multiplication. This is multiplying this. We don't have to put parentheses if they are different from another, right? So in this case, this is going to be 1 over, looks like, that's 1 over sine. That's right. That's the reciprocal identity. And then we have tangent is sine over cosine. Oh, hold on, real quick here. Can I cancel something out here? Yep, sorry, right there. Sine is gone, so it becomes 1 over cosine. Now the question is, do I leave it as 1 over cosine? Do I change it to secant? It doesn't matter, but usually we like to keep it in terms of the cosine, sine, or tangent functions. If you can do it cosine and sine, that's perfect. Okay, there it is. There's my simplified form of all that. These guys are multiplying each other. This is just one trig function. Okay, let's go with the next one here. Ooh, this is a ratio here. So let's see, cotangent is cosine theta over sine divided by, and tangent is sine over cosine. We have ourselves a complex fraction. I know what to do here. What we do is we keep the first fraction of the number on top exactly the same. Top fraction remains the same. Change this to multiply, and what we do is we take the reciprocal of this one. So moving this over. There it is. I keep it as, oh, now we're just multiplying these out. So cosine theta over sine theta. Can I keep it like that? Yes. Can I change one of them into, can I change the top? Let's do this one here. I'm going to put a new slide in because this is kind of important to see. So the question is this. I have, my final answer is sine squared theta over cosine squared theta over sine squared theta. Can I keep them like this? Absolutely. Right? Can I simplify it? Yeah. Actually, I can make it into just tangent, cotangent, right? Isn't this just cotangent squared theta? Isn't that weird? That cotangent divided by tangent actually makes cotangent squared theta. Okay, could you have made some other variations? Yes, you could have. So that's why, like, when you simplify it, it could be all sorts of different ones. So this one, I could have just made it like this. Tell me if you guys agree there. That's a simplified form. Okay, then the other one was, instead of changing it to sine squared theta and changing it to that, I could have just kept the sine squared the same, and I changed this guy into my trigonometric Pythagorean theorem identity. So all those, technically all those would be considered simplified forms. All right, this one would not be considered a simplified form, right? Because it's a complex fraction. It's not in terms of sine cosine. Okay, let's go some more. I think you'll get the flavor for it and the hang of it as we do some more. Okay. C, cotangent theta minus cosecant theta. Can you simplify this out? Let's go with it here. So cotangent is cosine over sine minus, and then cosecant is 1 over sine. And the question right here is, do we have common denominators? Remember, in order to add or subtract two fractions together, I have to have common denominators. Do I have them here? Absolutely. So that means my common denominator is sine theta, and the stuff on top is cosine theta minus 1. There it is. There's my simplified form. Okay. And let's go on with, hey, add, subtract, or multiply. Let's see this. Let's get a little more complicated. All right, so add, subtract, normally what we do is we just change everything into sines and cosines. If sine and cosine is already there, we just keep those guys there. But tangent, what is tangent? Tangent is, okay, so tangent is sine theta over cosine theta. Oh boy. These guys are not common denominators. But if I'm going to have fractions added together, I actually have to make common denominators. So let's go back to an algebra problem, kind of a little easy algebra problem. If I'm adding, let's say 1/3 plus, let's say 2/5. Okay, so 1/3 plus 2/5. What's my common denominator? 15, absolutely. So it's the 3 and the 5 multiplied together, is that right? 3 and the 5 multiplied together. And then we put the same common denominator over here. And then we ask ourselves this question, right? What number multiplies 3 to give you 15? 5. And then 1 times 5 gets put over here. Right? So same thing here. What number times 5 gives you 15? 3. We kind of keep it in our head, is that right? And we say 3 times 2 gives us 6. And once that happens, then we can add these guys together. Okay, we're going to do the same thing here with trig functions. You ready? I need a little more space. All right, here's my space. That's some interesting stuff there. Okay, whatever that was. Okay, so here it is. We need to get common denominators. What is the common denominator between these two fractions? Well, look at my denominator and looking over here. I see a sine theta and I see a cosine theta. Those two are going to be my common denominator. So sine theta, it doesn't matter what order you go in. I got sine theta and cosine theta. Okay, so let's see what happens here. In order, you know what, let me do it the way we did the 5 and the 15. I'm going to write it like underneath here, like that. Cool. That's a little easier to see. So what have I multiplied sine to give me sine times cosine? In our heads we say cosine, that's right. So what's cosine times cosine? It's cosine squared theta. All right. What do I multiply cosine to give me sine theta cosine theta? Sine, what is sine squared, or sine theta times sine theta? Okay, perfect. Hopefully that made sense there. And we go ahead and finish up. Here it is. So sine theta cosine theta is my common denominator now. And on top I have cosine squared theta plus sine squared theta. And someone should be saying something right now. The numerator. The numerator is just what number? Cosine squared theta plus sine squared theta is equal to 1. There it is. There's my simplified form of that expression. All right, and of course, I got a few more for you. So let's go with it. All right, can you do this one here? And give you a little bit of time. See if you can do this one before I finish. All right, let's go with it here. So let's see, one over cosine is there. And then, whoa, hold on. Cosine and cosine. I already have everything in terms of sine and cosine. I guess what I'm going to do here, I'm just going to put a little 1 right here. So now, how do I get common denominators? Oh, that's right. Hold on. If one fraction already has a number there, and the other one only has a 1, that means this one right here becomes the common denominator. Okay, 1 times what gives you cosine? Cosine times cosine is cosine squared theta. Perfect. Let's go from there. My common denominator is cosine, and on top I get this. And again, some people should be saying, Mr. Ngio, I know this. This is something that we've studied before. Okay, can you leave it like this? Technically you can. This will be correct. This will be just fine. If you want to simplify it, so instead of my equal sign over here, what I'm going to do, I'm going to put an or statement right here. So that would be correct, and this would be correct, right? Because 1 minus cosine squared theta is equal to sine squared theta, and those two equally correct. My gosh. No. I'm so sorry. All right, let's handle this one here. So 1 over cosine plus 1 over sine. Let's go with, you guys are experts now. So common denominator is sine theta, cosine theta. Perfecto. Sine theta, cosine theta. Okay. What we need for the first one, we already have cosine there. So the multiplier would be sine. For this one here, we already have sine. So the new stuff is cosine. Cosine times 1 is just cosine. Voila. And the final answer is sine theta plus cosine theta. On top is just sine theta plus cosine theta. And that is the easiest form right there. That is it. Okay. Next. They're just moving slow for some reason. There it is. Okay. All right. How about this? D. It has cosine theta plus 2 in parentheses, and then cosine theta minus 3 in parentheses. I guess we're going to multiply. So go back to your algebra skills and you ask yourself, when I saw something looks like this, what did Mr. Grant tell me to do? Yeah, I think so. It was something called FOIL, is that right? Multiply the first ones out, multiply the outside ones, multiply the insides, and then multiply the last ones. Perfect, that's exactly what we do here. So here it is, cosine theta times cosine theta is cosine squared theta. And outside ones here, cosine theta times -3. Whoa, that's interesting. The inside ones would make us 2 cosine theta. And the last ones here, 2 times -3 is -6. Are there any like terms that should be added together? Absolutely. The -3 cosine theta and plus 2 cosine theta. So here it is. The form is cosine squared theta. Let's combine the two middle terms together, which is -3 plus 2 is a -1, so it'll be minus cosine theta minus 6, and all good to go. All right, and if you know the fast way to do this right here, So if you remember this from algebra, how did you guys do like x minus 5 to the second, like really, really fast? Okay, if you don't do that, go for it, okay? If you don't, that's okay. We're going to do it this way. So I'm going to say if that's a 2 here, if there's a power of 2, that means there are two parentheses that are exactly identical. And then we're going to use the exact same process. Here we go. So cosine times cosine is cosine squared. This guy will give me, oh, one's a cosine, one's a sine. So normally we write sine first. Customary, it's not that it's incorrect, but that's just the way it has been. And then we multiply these guys. The inside one, sine times cosine, will give us another sine. Theta cosine theta. And then the last one here, sine theta times sine theta gives me sine squared theta. All right, in like terms? Absolutely, right in the middle. So final answer, here it is, cosine squared theta. And there's one of these and another one of these, which makes two of these. Boom, and we get ourselves that right there, and we are done. That is the final answer there. Okay, let's keep on going. All right, these ones will get just a little bit more complicated. Not that much, just a bit. So, all right, it says this. It says simplify the expression by substituting the trig function. And when you substitute the trig function, you're going to find some substitutions that you can actually make. Okay, we'll do two of these kinds right here. So I have a square root of x squared plus 1. What I'm going to do is I'm going to substitute tangent theta for the x and see if I can simplify it down a little bit more. All right, so let's go with it. So I'm subbing, so this is still a square root. Technically, just a positive square root, right? And I'm substituting a tangent of x. And I like to do this. I like to put like whatever I'm substituting, I like to always put in parentheses because then I know if I can backtrack in my notes, I know what I actually substituted. Okay, so there it is. And that I know is the same thing as this. Right? I can write it without parentheses here. Oh, sorry. Yeah, I made a mistake here. This is theta, right? Not x. That's theta. That should be theta right over here too, and plus 1. Okay, anybody know of any trigonometric identity that will simplify tangent squared theta plus 1? Tangent squared theta plus 1. Anybody seen anything like that before? Go back over here, maybe. Not that one. Definitely this one. That is tangent squared theta plus 1 is the exact same thing as secant squared. All right, and the question is, how's that going to help us out? We will see. If I can take two terms inside a square root, and I can actually make them into one single term inside a square root, that is actually a perfect square. Can I take this out now? Absolutely. There it is. I've simplified that out to the point that I can get it even out of the square root. That's cool. Okay, one that's a little tiny bit more complicated, not by much, but just a little tiny bit more complicated. Dunk. All right, here it is. Now the expression inside the square root is a 4 x squared plus 100. Can I simplify this out somehow? Let's go with it. So I have myself this. I have myself a 4, and I'm going to substitute a 5 theta into here, squared, and I got to extend my line now. I'm going to add 100. Okay. Okay, if I'm squaring that, notice the little 5 in front right here, right? So that because of that 5 there, I have myself that 4 that's there. If I square the 5, that gets me 25 now, right? And then tangent, that's just going to be tangent squared theta, and that's 100. Okay, man. Let me keep on going. Let's see if something simplifies here. Yeah, that's right. Hold on. 4 times 25 is 100. Got 100 tangent squared theta plus 100. And the question is, how do I simplify this? How do I shorten up as much as possible? You know what I can do? Notice I have 100 over here and 100 over here. I'm going to factor out 100 out of both these terms. Then I'm going to be left with tangent squared theta plus 1. And if that's the case, tell me if you guys agree here. 100 is a perfect square of 10, isn't it? 10 gets to go outside of the square root. And this one I think we've seen before already. I'll just finish it off from here. If that's the case, that means this is the same thing as secant squared theta. And now since I have a single term that's a perfect square inside the square root, it gets to go out. And that is my simplest form I get out of this. Perfect stuff here. Okay. And then we have the last section here. This is the last other kind that we have. All right. So exercise 5, it says show that the following is an identity. Whoa, okay, so remember how we used to simplify? This time we want to know, we want to show that the right side and the left side are exactly the same. So now notice students kind of get mixed up. We're not solving anything. We just want to show the right side and the left side. If you simplify it down, we'll simplify pretty much to the same thing. So here's what we do. And for starters, if this kind of will help you, just kind of put a bar line all the way down like this. So they're saying, look, I'm not moving anything to any side. I'm just simplifying the right side, simplifying the left side. And let me make this bar line just a little shorter. I want to show something at the end here. Like that. Okay, so let's go for it here. So notice the left side, that one is actually pretty complex. On the right side is just sine theta. That's easy. So I'm going to take the more complex version here and say, okay, if that's cosine, cosine stays cosine. And notice what I'm really doing is I am just simplifying each of the sides now, something I've done before. Tangent is sine theta over cosine theta. And what I normally like to do, put a little 1 if I'm dealing with fractions. And what do you see happen? The cosine thetas are gone. Okay, I am left with just sine theta. And what I can do is I can bring this one down, sine theta. And then I get to actually put an equal sign here. There's my equal sign. That's why I left a little room, didn't put the bar line all the way down. Looks simple enough. We'll get to more complicated. But at least for starters, there it is. I have just proven that cosine times tangent is the same thing as sine theta, because by simplifying it, both sides turned out to be the same thing. Okay, and in the old trigonometry books, up until I think like the 1970s, whenever we did this, the old trig books, they always put this in there, and it was kind of cool. It was QED, boom, QED. And it was a perfect thing, a cool thing, but I'm not going to tell you what it means. So what you have to do is maybe when you get home and you're bored, if you're bored this weekend, you know, like what am I going to think about? You know, Hipparchus was thinking about trigonometry on a Saturday morning, right? So you figure, okay, Saturday morning. Oh, let me put it down here. If you have this random thought and say, I wonder what QED stands for in terms of trigonometry. And then if you do find out, tell me on Monday. We'll go from there. It'll be just one of those like, I wonder what that means. Have a Hipparchus moment here. Okay, let's go with B. More complicated, but still pretty cool. All right, this one is secant theta over tangent theta. Is that the same thing as cosecant theta? I don't know, but both of them look pretty complex to me. Okay, so we're just showing that the right side and left side are the same. You don't have to put this bar line down. It kind of helps if you're just starting out, but if you're just like, no, I'm cool like that, don't put it down. But let's deal with this one here though. So let's see, I'm thinking secant. Secant is 1 over cosine. Okay. And then tangent. Tangent is sine over cosine. Oh, that's right. Hold on. I know what to do here. What happens if you have two complex fractions and the denominators are exactly the same? Perfect. I can do that. Is that right? So if those denominators cancel, I'm left with 1 over sine. Now you have a little choice here. You can do one more step down here. You can make this into cosecant theta, or you can just bring this down and just say, hey, cosecant theta is actually 1 over sine. And it doesn't matter how it ends as long as you have made equality between the two sides. And of course, you're going to write QED. And then do you have to put the dots in there? No, you don't. Just write QED. All right, and the last problem of the day. Of course, it has to be a little more challenging, difficult one. All right, if you got this, can you guys try to do it yourself? Go. Give you guys 30 seconds. I'll start it myself. All right, I'm going to start here, and I'm going to be sophisticated. I won't put the bar line down. I'm going to just sort of work my way through this here. So we're saying all that equals all this. It means the same thing. Okay, let's go for it here. So secant. Secant is 1 over cosine theta. And cotangent. Cotangent is cosine over sine theta. I know that. And then this is just sine. Okay, so I'm going to work just a little bit more on the side. It doesn't matter which one you work on more, just that's the way you're gonna get it. Okay, so I'm thinking this right here. I'm thinking this and this cancels. So I'm left with 1 over sine theta minus sine theta. That's what I'm thinking here. Okay, I've simplified this out. Let me walk over to this side over here. Just say to myself, is there any, can I simplify this any? That looks pretty simplified already, huh? It's a single fraction. It's in terms of sines and cosines. It looks pretty good. Okay, so let me keep on working over here. Let me keep on working here. Let's see. I think I'm going to have to make this guy into a fraction as well. What is my common denominator? Sine, of course. Okay, so this guy stays exactly the same. Oh, this one's going to change, huh? This is going to change into a sine as well. But what do you multiply 1 to give you sine theta? Sine theta. What's sine theta times sine theta? Sine squared theta. And I think we are going a certain direction here. So hold on. If this is true, my denominator is almost done. And I got this. That's so cool. Hold on. So on the top, I have 1 minus sine squared theta. And if I had some room down here, I probably would have converted it to cosine squared theta because my Pythagorean theorem identity. Is that right? Since I don't have any room down there, I'm going to do it the other way. I'm going to say, you know what? I'm going to convert cosine squared theta into 1 minus, because the whole point here is just to show that they are exactly the same. And what I write down, because we're going to be sophisticated trig students, I'm going to write QED. All right. And then after the 1970s, We actually didn't teach Latin anymore in our public school systems. It kind of went away. And then eventually the QED went away too. So there's a little bit of a hint right there for you. What does QED stand for? All right. Anyways, hopefully that was you learned something, and hopefully you enjoyed it as well. Here, I wish you guys a wonderful weekend, and I'll see you guys on Monday.